NASA's Space Shuttle is the most complex machine ever built, making it one of the world's most expensive vehicles. But then it does travel 25 times faster than a speeding bullet, and it carries cargoes worth tens of millions of dollars. It's the world's first reusable spaceship. On each mission, it flies around 6.5 million kilometers. But no matter how clever the rocket scientists behind it are, this incredible feat of engineering wouldn't have been possible without a church organ, a German U-boat, tram tracks, a camera, it's mega, and a cannonball. The Apollo moon missions were a resounding success. But even as man walked on the moon, the question was, what would NASA do next? The answer was the Space Shuttle. It launches into the Florida sky from the pads behind me, and as the world's first reusable space vehicle, it's made the final frontier just another destination. A fleet of 5 shuttles has blasted off from the Kennedy Space Center more than 130 times. They've delivered well over 1,000 tons of cargo, including most of the International Space Station and the Hubble Telescope. Not bad for a delivery truck, albeit quite an expensive one. A new one will set you back a cool $1.7 billion. And taking it out for a spin costs about $450 million. But NASA designed the shuttle to reduce the cost of space exploration, so the shuttle is reusable. An ingenious jack of all trades, part plane, part rocket. I've come to look behind the scenes. Only astronauts or rocket engineers get close to the shuttle. This is the place where it starts, so next stop, space. But as they prepare for the shuttle's last ever launches, NASA has given me special access to see how it really works. To get to grips with the shuttle on a much smaller scale, the gift shop comes in pretty handy. What most of us think of as the shuttle is this bit, the white plane that carries astronauts and cargo. It's actually called the orbiter, and that's the bit that goes into space. At the back, it has 3 engines. They're big and they're thirsty, and the fuel for those is stored here in this orange fuel tank. But even together, that whole combo isn't enough. So, 2 solid rocket boosters are fitted to the side to provide more thrust. So that's 2 different forms of propulsion going on. The orbiter's 3 main engines burn furiously during the shuttle's 8.5-minute ascent into orbit. They're extremely powerful, 37 million horsepower to be precise. And they propel the 2,000-ton shuttle up to 650 kilometers above the Earth's surface. NASA has allowed me into the workshop where they overhaul the engines.
This is our main engine shop.
This is where it all happens.
This is where we prepare all these motors after they've flown to reinstall and get ready to go again.
And these are they. Mike Cosgrove is no ordinary grease monkey. He's one of NASA's elite rocket scientists.
These are the next set of engines we're going to be installing. We're finishing up the processing on those. They've flown and gone through our shop here and been completely refurbished, and we're just putting the final touches.
So these are being used next?
This will be used next.
This isn't a one-shot deal, is it?
No, this is a reusable engine. Some of these motors have flown up to 25 times.
4 million miles
per trip.
This could be 100 million miles on.
Absolutely.
Probably time for service. These engines don't just travel enormous distances, they withstand extreme temperatures. Without any protection, they would self-destruct. Temperatures exceed 3,300 degrees C, or 6,000 degrees Fahrenheit.
At 6,000 degrees, what would they do?
Normal metals would melt.
Yeah.
Gone. And that is a problem. Engines that melt will never do the job they're supposed to do. It's like trying to make a kettle out of chocolate. And we start with the very definition of uselessness, a chocolate kettle. Chocolate kettles, of course, famously useless because in order to heat water to be hot enough to make a decent cup of tea, well, on the way, you'll melt the kettle. Chocolate is designed to melt in the mouth. In other words, at just below body temperature. So just to prove the point, I shall now try to make a lovely cup of tea. Yeah, clearly already it is having trouble. Yep, its reputation is clearly deserved. Useless. NASA's shuttle engineers faced the same problem. Engines made of most metals would melt at operating temperatures. To stop this from happening, the rocket scientists turned to much simpler machines. Ones that blasted air through church organs back in 19th century Britain. And this is the job those machines had to do. Right, to work. This is the lever, those are the bellows. I pump the lever, it puts air into the system. And there you have it, the original Hammond organ. You see that? Yeah, okay. Can resist it. Of course, inevitably, after a time, along came a machine to replace, well, me, the person who pumps the organ. In the 1880s, the internal combustion engine was still in its infancy. The one first used to pump air into church organs introduced an ingenious new invention. And it would have been a machine very much like this one that replaced me, driving the bellows to provide air for the organ. It's a single-cylinder internal combustion engine. But it had a problem, like all internal combustion engines, and the clue is in the name, internal combustion. It's an explosion going on inside it, here. And that makes the engine hot, dangerously hot. So, it's jacketed with water. There's a water jacket around it. Another cylinder full of water to cool. Cold water is constantly circulating round the hot engine, removing the heat. This was the first cooling system for an internal combustion engine. It's a primitive version of what NASA uses on the shuttle. But while water can cool one of these engines, it's never going to do the job for NASA. At shuttle temperatures, most metals would get so hot, they wouldn't just melt, they would vaporize. So the rocket scientists had to take engine cooling to a whole new level. Luckily, NASA already had a great coolant on tap. Inside the giant orange tank is the fuel, super cold liquid hydrogen. At minus 253 degrees Celsius, it is perfect for cooling engines.
This is where you see the big fireball come out the backside.
Yeah, this is a bit we've all seen on the television. So it's at the back.
How are we going to cool this bad boy down? Well, what we're going to do is we're going to take a tap off of that liquid hydrogen that's being pumped around through the engine, and we're going to duct it down the side of the nozzle here through these distribution tubes. It's going to fill up this manifold, and then it's going to flow back up through 1,080 tubes into the main combustion chamber and burn it.
So the actual fuel that you're using is sent along these pipes here, and of all of these, I thought these were just marks. These are actual
These are tubes. These are
which cools this down.
Yes, this
protects it from the heat of the engine.
Correct.
And then it goes in and is burned.
Correct.
Which is one of the secrets to the incredible efficiency then of this engine, because you're actually using the fuel before you've burnt it.
Correct.
The reason shuttle engines don't melt is because of a principle first used in an engine like this to drive the bellows on a church organ. A cooling system, the removal of heat. The shuttle's fuel cooling system is so efficient, it keeps the engines at a cool 54 degrees Celsius. But can all this rocket science help me boil water with a chocolate kettle? To test NASA's system, I've built a radical new prototype. What we have here is something pretty special, because this is a chocolate kettle inspired by NASA. I've gone one better, in fact. This isn't just a chocolate kettle, it's a chocolate ice cream kettle, because that's what that is. Chocolate ice cream. The challenge is to stop my ice cream from melting as the water heats up. Here's how it's working. This is the fuel for the burner down here, liquid propane. It's rushing along this narrow tube here, up here. Just like the shuttle, I'm using freezing cold fuel to do the cooling for me. It then carries its way around here, down here, into the burner. That's the actual fuel I'm using. Because it's staying cool up here, despite this being full of now boiling water, my ice cream is staying frozen. It's NASA, that is. 100 degrees on the inside, below 0 on the outside. But it still isn't a perfect kettle. One thing I didn't design in any way of pouring it out. That's a refinement. I'll work on that. But just like my ice cream, the space shuttle main engines don't melt, even though they should be getting really, really hot. But even the staggering power produced by the most efficient engine in the world isn't enough on its own to get the shuttle into space. At liftoff, the shuttle is just too heavy. The engineers needed more power, but they had to limit the weight. It's a tricky thing to get right. To get more power, you need more engines and more fuel. More engines and more fuel means it's heavier. So the shuttle is fitted with these boosters. These are solid rocket boosters, or SRBs, and they have a great power-to-weight ratio. And as the name suggests, the fuel they burn isn't liquid, it's solid. And it's very, very explosive. The height of a 15-story building, these are the largest solid rocket boosters ever flown. When the fuel is lit, all those elements produce about 1,300 tons of thrust, about the same as 17,000 Formula One car engines. To get that amount of power, the fuel has to burn at incredible temperatures. The secret ingredient takes us back to tram tracks. In the 19th century, tram tracks were just bolted next to one another, and the gaps between them made for a bumpy ride. Then in the 1890s, German chemist Hans Goldschmidt invented a way to weld tracks together. Goldschmidt discovered that he could create an intense heat by burning something you might not expect to burn at all: aluminium. First used in Essen, Germany, aluminium welding made for a much smoother ride and revolutionized tram lines across the world. It's the intense heat of burning aluminium that NASA exploits. Burning even a small amount can be hot enough not just to fuse steel, but to cut through it, which is why I have one of these. It's an aluminium lance, made out of aluminium foil, as you'd find in the kitchen. Lots and lots of it rolled very tightly here into fine tubes, wrapped in yet more aluminium foil. Obviously, this is something you don't want to be trying at home in your kitchen, but you probably don't have the other ingredient you need anyway, which is compressed oxygen. That's over there in the tanks. So, oxygen flows along the pipes, along my aluminium lance. Up here, I ignite it, the aluminium burns. In theory, once lit, this should burn at least 2,500 degrees C. So it should be around about half as hot as the sun. But can my homemade lance make an impact on solid steel? Right, only one way to find out. Enough talking, let's do it.
sometimes you can look at theories and numbers on paper, and sometimes you just need to see solid evidence. And I think that counts. Clearly, that was pretty hot.
Burning aluminium provides enough heat to cut through steel and weld tram tracks together. And it's the vital ingredient for the shuttle's solid rocket boosters.
Of course, the SRBs aren't just full of aluminium foil. There is other stuff in there as well, although you wouldn't want to wrap your sandwiches in any of it. Ammonium perchlorate to provide oxygen for combustion. Iron oxide, rust, to help it burn.
It's the powdered aluminium, though, that creates super high temperatures. High temperatures turn the solid fuel into vast amounts of gas. And it's this gas that makes the rocket move. Because when a lot of gas is forced through a narrow nozzle, you get thrust.
It's the same thing that happens when you let go of a balloon. The air inside is squeezed and shoots out this way. So that's a push. There's an equal and opposite reaction, which means a push this way. So the balloon goes that way. Sorry.
The challenge for NASA was to make a rocket that has as much thrust as possible right at the start, when the shuttle is at its heaviest. In an attempt to find out how they do that, I've asked rocket man David Beaton to help me build my very own Great British Space Fleet of 2. And just like the shuttle's rocket boosters, we are using solid fuel made with powdered aluminium.
So this is the fuel. Can I hold it?
Yeah.
It's not dangerous?
Nope.
There's the same amount of fuel in each rocket, which will burn along its entire length. But the fuel with the hole down the middle should burn faster. More fuel will be on fire at once. So the rocket should fly faster right from the word go.
So because that's burning faster, the same load...
The same load, yeah.
Burning faster,
Yeah.
the power is given more quickly.
This will give a real good peak of power, and as it burns out, it will also progressively increase the thrust as well. Yeah.
And will that make a visible difference?
Oh, yes. Yeah.
Can we test
If
it?
we can.
Can we have a race?
I would think so.
So, other than the position of the ignition groove and the colour, these two rockets are identical.
If I drop this, it's bad, isn't it?
It could be bad, yeah.
Okay.
Yeah.
So to get this right, this one has the faster burning charge.
That has the faster burning motor. That's yours.
Okay. Okay. Rocket science.
That's okay. Yeah.
Oh, yeah.
Job done.
This is mine. Moving that one.
We'll arm the system. Five, 4, 3, 2, 1, go.
In just 10 seconds, the red rocket shoots 600 meters into the air.
I think that was quite clear that the red one was a lot faster.
The red rocket's fuel burns much faster, because more of the fuel is on fire at once. This means more hot gas is produced in a shorter time, which gives this rocket more thrust. The blue rocket eventually reaches roughly the same height, but it takes much longer to get there, even though it had a bit of a head start.
It was visibly quicker.
It was,
And that's just a faster burn. That's what
That's just the fast burn.
But same energy release, just
Same
released
energy
more
release,
quickly,
just
isn't it?
released more quickly.
Got to find them now, obviously.
Yes.
Yeah.
NASA's shuttle engineers need maximum thrust, so they go for a bigger, faster burn, like the red rocket. At launch, each booster is burning fuel at the unbelievable rate of 5 tons every second. They burn for about 2 minutes. Then they're jettisoned. "49 kilometers up, they fall away from the shuttle and back to Earth. They crash land into the Atlantic Ocean. Here, and this is the beauty of the system, NASA picks them up for refueling back on dry land. So, thanks to a welding technique that smoothed out tram journeys, the thrust provided by the solid rocket boosters is enough to get the shuttle off the launch pad and on a journey of its own. Hundreds of kilometers into space. But the rockets are so powerful that they create a very dangerous problem of their own. At liftoff, the exhaust gases that generate thrust also generate phenomenal sound energy. This is so powerful, it can have fatal consequences. And this is the launch pad where it all happens.
During a launch, this place is just alive with energy. Flames, searing gases, incredible amounts of noise. I'm underneath where the shuttle sits on the launch pad. This is the flame trench. I can only be here because the shuttle isn't in place right now. You certainly wouldn't want to be here when the countdown hits 0. And this trench was used in some Apollo missions as well. So to think of the incredible amounts of energy that these walls have taken over the years, it kind of boggles the mind.
The firing rockets create a thunderous sound that slams into the bottom of this trench. This sound is energy. And systems engineer John Lorch knows how powerful this can be.
Even way back, 3 miles away, you can feel that energy just popping in your chest, you know, and it's just amazing the amount of energy.
Unchecked, all this energy would bounce off the ground, straight back up towards the shuttle. The vibrations would be so powerful, they would wreak havoc. On the first ever shuttle mission, they ripped heat-resistant tiles off the surface of the orbiter. That time, the orbiter returned to Earth safely, but it could have burnt up on re-entry.
So the engineers needed to find a way to protect the shuttle from reflected energy. To do that, they had to absorb the sound energy that roared down here and then bounced back up and hit the shuttle itself.
Back at the Hammond Space Centre, UK, I can't replicate the shuttle's thunderous sound, but I can give you a taste of its destructive power.
I'm going to build a wall here, and then I'm going to knock it over with a pulse just of air. Like that, only bigger, a lot bigger. I'll just use the half one on the end. Look, I made a neat job of that.
That's the wall built, and over here is what I hope is going to blow it over. A vortex cannon. First, we need to do a little test run.
3, 2, 1. That is up there amongst the most amazing things I've ever seen.
An explosion in the base of the cannon creates a single pulse of air the shape of a donut. Unlike sound that moves in a wave, The vortex flies through the air like a missile. The vortex has a lot of energy, but can it knock over my wall?
So Jim's now charging it with acetylene, ready to make our explosion. Don't overdo it, will you?
This is going to have to be one hefty puff of air.
Thank you very much. If we're ready, everyone, in 3, 2, 1. It's just air.
Slow motion allows us to see the vortex as it travels through the air at over 320 kilometers an hour. And as you can see, it creates a fair amount of destruction. The Shuttle's problem is much bigger. Its exhaust gases jet out at about 4,000 kilometers an hour, producing vast amounts of sound energy as vibrations. The engineers needed to find a way to protect the shuttle. NASA turned to a system that connects the shuttle to U-boats via bubbles. Acoustics expert Tim Layton from the University of Southampton shows me how. What we have here is our very own mini sonar system. A tube of water, a speaker at the bottom that plays cheeps of sound, and at the top, a special underwater microphone that will pick them up. You can hear the sound cheeps, and they're represented on screen here.
I'm going to introduce bubbles in here, because bubbles are really powerful at absorbing sound. So here we go.
So this is the key thing to watch.
That cheep is going to disappear.
All right.
So here we go.
So you're literally just blowing bubbles into
Just
it with the
blowing,
machine?
yeah.
All right, I can hear that.
But look at the screen.
It's gone.
The bubbles that you can see in the pipe are killing off that sound entirely.
We're still playing the sound cheeps through the water, but even the smallest bubbles are stopping the microphone from picking them up.
There's nothing
And it's
in
still
there
gone.
now.
We're still
Are
waiting.
they enough to stop it?
Yep.
But there's hardly any. So these tiny,
Yep.
almost microscopic bubbles
Killing
are
off all that
completely
sound.
killing the sound on there.
The bubbles soak up the sound by getting hot.
So literally then, the sound leaves here, which is just
Yep.
this wave, this movement coming up through here.
Yep.
When it encounters bubbles of air in the water,
Yep.
the wave squashes the bubbles
Yep.
of air, that heats them up.
Yep.
So the energy in the sound wave is turned into energy
Heat.
in heat.
So bubbles absorb sound. But how does that help submarines? World War II, the German U-boat fleet is under attack. The Germans want to make their subs untraceable to the Allied destroyers and their sonar systems. The Allied sonar worked by sending out sound cheeps from their ships and then waiting for the echo to bounce back from a solid object. This could tell them where the German subs were. If the Germans could absorb the sonar cheeps, no echo. They would be invisible. So they created rubber tiles to glue to the sides of their subs. Tiles with bubbles in them.
This is a genuine World War II lining from a German submarine. And you see it's stuck onto the submarine this way. This side is smooth, but this side has holes in, has voids in.
The holes trap air, creating thousands of little bubbles.
When a sonar ping comes and hits this, these absorb the sound in the same way that those bubbles did.
So bubbles can make German U-boats invisible. But the shuttle isn't underwater, obviously. And it has a bit more than just cheeps of sound to deal with. To absorb the phenomenal noise of firing rocket engines, NASA turned sound absorption on its head. Instead of air in water, They put water in air. Tim's got another tube with just air in it. We're still sending cheeps of sound through it. But this time we're going to try to block them with a mist of water droplets.
This one into this one,
Water into ice.
Okay, so pour that in there, and it makes fog. Can't really see where I'm pouring. Hopefully that's into the tube. Yeah, it's going in, isn't it? I feel like a wizard.
And my spell seems to be working.
Oh, look at that! Absolutely knocked it right back. So this is just fog. I'm not tipping the actual water in.
The microscopic droplets of water in the air are vibrating, turning the sound energy into heat. NASA protects the orbiter in pretty much the same way. Though needless to say, NASA's system is a bit more complicated.
It looks like a warehouse. It's actually the mobile launcher platform. The shuttle assembly sits on top. Those three, 1, 2, 3, they're the rainbirds. And at peak flow, 9 seconds after launch, water hurtles through those at a rate of 900,000 gallons, that's 3.5 million litres a minute.
Releasing so much water so quickly through the rainbirds forms millions of water droplets suspended in air. And it's these water drops that absorb the phenomenal sound energy. The system for unleashing that amount of water is unbelievably simple. A water tower.
At heart, this is essentially a really big version of the kind of water tank you'd see outside a town or a city.
This is really just an elegant, simple design to get that flow rate we need.
When the valves open, more than 1 million litres of water plummets. It sprays beneath the rocket engines and absorbs the thunderous sound. So, can water work against the vortex cannon?
Time to see if what's good enough for the shuttle is good enough for my wall. First, obviously, we've got to rebuild it. Lovely.
Next, we need water.
This is our rainbird. Pretty simple setup. I'm not saying every home's got one, but essentially it's got pumps here, pumping water from the lake up through those pipes and out to the top there, where a sprinkler arrangement creates basically a wall of water. So let's test it. We need to get it into position. Bring it in.
The blast I'm about to fire has exactly the same power as before. But this time, there's a curtain of water between the cannon and the blocks.
Okay, if we're ready, everybody, in 3, 2, 1.
In slow motion, you can see how the pulse of air hits the water and loses energy.
Well, look at that. I think we can safely say, top marks, NASA, well done. Their theory works, as I just proved. They'll be grateful. I mean, it really did work. By using billions and billions of drops of water to disrupt the energy pulse, the NASA engineers are able to protect their precious orbiter and its payloads. And it's all thanks to the power of the bubble.
Eight and a half minutes after liftoff, the orbiter is more than 300 kilometers above the Earth. It's in space. Only minutes later, the crew is getting ready to start its mission.
The orbiter was designed, basically, to be a delivery van. A very expensive, very technologically advanced delivery van. Its job is to deliver things into space. So far, it's put satellites, telescopes, and most of the International Space Station up there.
But you can't just pop open the back and pull out your cargo. especially when it's likely to be a satellite, chunk of space station. Not the easiest objects to move, and quite expensive if you drop something. So every shuttle cargo bay is armed with a helping hand. Don't worry, I'm not about to be offloaded into space. This is a full-scale model back at Kennedy.
Even if the astronauts could physically lift and manhandle the cargo, spacewalking is very dangerous. So NASA turned to robots for help, specifically a robot arm called the Canadarm, built by those famous space scientists, the Canadians. They faced a real problem. How do you grab hold of something in space without accidentally knocking it across the galaxy? The answer was found in a camera lens. Camera lenses, just like our eyes, have irises in them that control the amount of light allowed through the lens. In a camera lens, they're made up of a series of interlocking metal plates, which, when twisted, change the size of the aperture or hole in the middle. But how did this end up on the Canadarm on board the space shuttle?
The first designs for the Canadarm gripped objects much like a hand would. But engineers quickly realized that there was a fundamental problem. The smallest of accidental nudges could send any cargo hurtling off. There's no air resistance in space, so once something starts moving, it doesn't stop. For some reason, NASA wouldn't let me play with their $100 million arm in orbit. So, to find out just how big a problem this really is, I've asked Neil Billingham to introduce me to one of his robots.
Can I move it like that? Yeah. So that's forward. Ooh, it's faintly spooky.
What I'm doing is pretty much what shuttle astronauts have to do in space. And I'm beginning to get the hang of it.
See if I can scratch my nose a bit. It's annoying. It's the best thing I've ever played with. It's mega.
On Earth, the claw on the end can open and close, making it a perfect tool for grabbing things.
I'll close the gripper, and then the other one will open it.
I'm glad I didn't do that when my nose was in it. So this claw arrangement here, clearly a very useful multi-purpose device here on Earth. How would it work in space? Well, we can find out because I've constructed here my very own satellite.
The helium balloon does behave a bit like a weightless satellite in space. So it's very hard to grab hold of. And I'm not just making this up. Peter Stibrani is a Canadarm expert.
Okay, so it's in position. I'm going to go for a grip. Well, that's not worked at all. That's also given it a little bit of a shove. I presume in space that would be really bad news, wouldn't it?
Certainly, you could push your target away from you.
And if we were in space, that would have just kept going.
One wrong move on the real 15-meter-long arm, and I could send millions of dollars worth of satellite racing out of reach. Somebody would be cross. NASA needed a new way to grab hold of things in space. One with 100% accuracy. Then one of the engineers working on the robot arm had a eureka moment. A keen photographer, his inspiration was the camera iris. And I have a mini version of what he helped design to go into space. Like a camera iris, it rotates, but instead of interlocking plates, it has 3 wires that close in.
And almost straight away, I've captured what it is I'm after. I reckon... There's my space telescope. Cool. It took me seconds to do it. Why is it so much easier with that than it was with just an ordinary grab?
The initial volume that it can grab is very large. So all you have to do is make sure that your target is somewhere in there, and you don't have to do a lot of alignment.
The end of the real Canadarm is 20 centimeters in diameter.
So as long as I get it within that area,
Yeah.
it can only possibly be gripped because it just tightens it down and puts it in the right place.
And it could be at the wrong angle, it could be off, it could be backwards or forwards, and it doesn't really matter that much.
Once locked tight, astronauts can easily maneuver a chosen satellite. Since 1981, astronauts have used the Canadarm to grab the Hubble Telescope, transport over 200 tons of space station into orbit, and commute in style. Thanks to a simple camera iris, the Canadarm is now a vital part of all shuttle missions. But once the mission is complete, there's still the pressing problem of getting back to Earth in one piece. The return journey is one of the most dangerous parts of any shuttle mission. And it can be fatal, as every astronaut is all too aware. In 2003, the orbiter Columbia burned up as it re-entered Earth's atmosphere, killing all 7 crew members. The problem is the incredible speed. At re-entry, the orbiter is traveling at 27,000 kilometers an hour.
High speeds in space are not a problem. There's no atmosphere. But start hitting trillions of tiny particles in the upper atmosphere and things change. Hitting all those particles creates friction, a lot of friction, and that generates heat. Aeroplanes, missiles and bullets are usually streamlined so they can slip through the air, creating as little friction as possible. And early scientists thought that approach would work for rockets.
But in the 1950s, space scientist Harvey Allen realized that rocket speeds come with their own problem. Travel at 5 times the speed of sound and above, and the friction is too intense. No matter how sleek the design, no known substance could survive the heat for long.
Allen's solution was, at first hearing, pretty radical. Rather than make the nose of anything needing to re-enter the atmosphere sharp and sleek, he said to make it blunt, deliberately unaerodynamic.
And that's why the orbiter's blunt nose can be connected back to a particularly unaerodynamic flying object, the cannonball. We now know a round cannonball is not the perfect flying shape, but its ultimate aim is not to fly. It's to smash as much of something as possible. And that's exactly what Allen thought a re-entry vehicle should do: smash the air and blast it out of the way, not try and cut through it. This was throwing the usual rules of aerodynamics out of the window. But how does smashing into air help the orbiter on re-entry?
This is the University of Manchester, but it's a very specific little corner of the university because these machines are dedicated to serving another very, very special machine through there. It's a wind tunnel, but these winds will be traveling at hypersonic speeds, up to Mach 6.
That's 6 times the speed of sound.
Now, obviously, that kind of performance involves the release and control of stupendous amounts of energy, which is why the actual wind tunnel itself isn't as big as some you might be used to.
So, to go inside it, I have one mini orbiter with a pointy nose and one with a blunt nose.
How do I do
Kostas Kontis is the head of aerospace research. First, I want to see exactly why a pointy nose design is such a bad idea for the orbiter.
I guess it's got to be fairly firmly fixed.
Of course, because we don't want them to fly around during the air. It's quite dangerous.
What if this tunnel goes off while my hand's in there?
Probably you will lose your hand.
Literally just blown away.
Of course, yes.
I don't want that to happen. Let's get this done quickly.
At these speeds, you can only see what's happening with an elaborate system of mirrors, lenses, and high-speed photography.
So, if we can switch off the lights, please.
Yes. That's a lot of energy about to be released through there, isn't it?
That's right, yes.
A 6,000 kilometers an hour jet of air to be precise.
Fire!
That was strangely frightening. Right, well, let's get that image up and have a look. Right, so this is with a pointed nose.
That's right.
With this system, you can
Exactly.
actually see the shockwave.
The air around the nose is compressed so much that it forms superheated shockwaves.
It actually hits the wings. So that's the tricky part, because it's quite dangerous. The temperature will be very high.
So this shockwave, it punches through the air, the air goes over it.
That's right.
And it's actually, I thought that was good. Look, it's making a tiny hole, it's sleek. But where that line hits the wing,
Exactly,
there's
yes.
a lot of energy being deposited right
yes.
there.
The wingtips are exposed to high-speed air, so lots of friction. And at orbiter speeds, the shockwave itself reaches thousands of degrees Celsius.
So it can literally, because of the shape of its nose, it can tear its own wings off.
Exactly, yes.
And the wings are rather important. Up until re-entry, the shuttle has been a rocket. But now, it's a plane that has to glide back to Earth.
So entirely counter to what we would expect. The pointy shape doesn't work.
So how will the blunt nose fare?
Fire! Okay, that's it.
Okay, lights up. Right, moment of truth. This is where we see, hopefully, some difference. Go on, then.
Okay, let's press the button.
Okay. Whoa!
You see?
Well, that couldn't be clearer, could it?
With a blunt nose, the shockwave misses the wings completely and deflects high-speed air away from the orbiter's wings. So, no friction.
And it's completely counterintuitive. I just would not guess that if I was sitting down to design something to re-enter the atmosphere, I would immediately think, well, pointed is best. That runs against everything that your kind of instinct tells you.
So, thanks to a cannonball, blunt is best for re-entry. But as is seen in this actual footage from the orbiter's cockpit, the shockwave around the craft glows intensely. At Mach 25, it's superheated to 5,500 degrees C. It might not touch the orbiter, but as you can imagine, it still makes it pretty warm. So at NASA's Kennedy Space Center, scientist Martin Wilson is in charge of producing heat-resistant tiles to protect the space vehicle.
Heat. It's very hot. So this essentially is a kiln.
Yes, this is one of the kilns that we use in the various heat treatments of the tiles during manufacture.
And what sort of temperature is it in there?
The temperature inside the kiln is 2,200 degrees, about 1,160 centigrade. And these are actually the materials from which the tiles
you
are made.
picked it up.
It's pure silica.
But it's just come out of there.
It just came out of there.
Seconds ago.
Still very, very hot.
Have you got special hands? Can I do that?
No, you can do that and touch it only by the corners.
That's just come out of that kiln. That's astonishing. You can still see the energy that's bouncing around inside it.
Silica cools down very fast at its edges. But because the tiles are effectively a silica foam, they're also full of air, and this makes them great insulators. So, thanks to these heat-resistant tiles and cannonballs, the orbiter completes re-entry and glides in for landing. It touches down at just 350 kilometers an hour.
So, after a journey of some 4 million miles at about 23 times the speed of sound, the orbiter, the final part of the shuttle, is safely here, back on Earth.
Over 3 decades, NASA's shuttle fleet has traveled over 800 million kilometers. It's taken mankind into space to orbit our world and push the frontiers of our knowledge. And it owes its engineering DNA to a church organ, a German U-boat, tram tracks, a camera, and a cannonball.